Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Tonight, we have a wonderful opportunity to learn how stars and their planetary systems form from someone who is very much on the front lines of that research, Joan Najita of the National Optical Astronomy Observatory in Tucson, Arizona. Dr. Najita received her undergraduate degree here at Harvard in Cambridge, Massachusetts, and very early was recognized for her brilliance. She went on to take her doctorate from UC Berkeley in 1993 and followed with a postdoctoral fellowship at the Center for Astrophysics. She joined later the Space Telescope Science Institute in Baltimore, Maryland, and then in 1998 joined the astronomy staff at the National Optical Astronomy Observatory in Arizona. Dr. Najita is also a recipient of the Annie Jump Cannon Award for Outstanding Research in Astronomy. It is our great fortune that Dr. Najita is spending her sabbatical year here at the Harvard-Smithsonian Center for Astrophysics in Cambridge this year, and she's kindly agreed to explain to us tonight what astronomers are learning at last about the formation of stars and their planetary systems. In a recent presentation she gave at the Center for Astrophysics, Dr. Najita pointed out that when she was an undergraduate in the 1980s, there were no exoplanets. Then, when she was a graduate student, a few exoplanets were discovered and there was great excitement. And now, during her career subsequently, hundreds of exoplanets have been discovered, and a variation is so great that astronomers are often rethinking basics about how stars and planetary systems form. Since she's one of the pioneers in the analysis of the stellar disks and how planets form from that gas and dust, we're very honored to hear from Dr. Najita what astronomers know now and also what they're still trying to figure out. Welcome, Dr. Najita.
Thank you, Yvonne.
And we'll start right off. So how do stars form? Last, tell us.
Well, there's some things that we know and many things that we don't. But I do have a slide that we might have a look at because it illustrates some of the issues.
Okay.
So in the slide, we can see that the story of star formation begins in molecular clouds, which are not uniform media, but are very clumpy. And the densest clumps eventually become gravitationally unstable to their own mass, and they collapse. But because they start out with a little bit of angular momentum, not all of the material forms a centrally compact object, but object forms, but a lot of the material goes into orbit around it in a circumstellar disk. And so the star, as matter swirls in from the outer disk to the inner disk, it eventually makes its way onto the star, which is part of the way in which the star gains mass. And while the material is in orbit around the star, it's the raw material for the formation of planetary systems. So the story of star and planet formation are very closely linked in that way.
Evidently. Can I ask a couple of things just for clarification? First of all, what is the angular momentum? And then what's a molecular cloud?
Okay, so angular momentum, you may often, analogy that people make, an example I guess that people give, is a skater, ice skater who you may have seen in the Olympics. And when someone is rotating, you can rotate more slowly when your arms are out, but when you bring them in, then you spin up through the conservation of angular momentum.
Okay.
If that's an example. Molecular clouds are clouds of gas in our galaxy, that it fills our galaxy, and they have molecules in them, simple molecules typically, like molecular hydrogen, 2 hydrogen atoms making a molecule, or carbon monoxide. Those are common molecules that are seen in molecular clouds. And though the gas in these clouds is the material from which stars and eventually planets can also form.
Okay, and that kind of gas, is this just sort of everywhere, ubiquitous in the universe, you think?
Oh, well, let's see. It's not uniformly everywhere.
Yeah, I mean, not, yeah, right, not
But
spread out, but that's the stuff.
There are clouds in our galaxy, and then many other galaxies also have molecular clouds. So it's not restricted to our own galaxy by any means.
Yes, right. But I meant that's the makeup in general, that this is very widespread. Okay, and so they collapse and you get a disk.
Right.
Right, and it's pretty much the case that out of that disk you'll get planets.
That appears to be the case.
Okay, is that new? That sense that's new?
No, I think it was quite a surprise how that story has developed. When, as you mentioned, when I was a grad student, we knew of no extrasolar planets, and I think at the time people were pretty pessimistic that any would be discovered. So it's been quite a revolution that not only have they been discovered, but it turns out that they're very common.
Yes. So is this sort of like the discovery longer ago that, oh my gosh, we're an ordinary star among billions and billions of stars, and we thought we were so special. But that finding, and that was of course very long ago, but is it similar to that finding the planets all over the place were?
Well, let's see. I guess we can answer the question of whether planets we're alone in the sense that there are no other planets in the universe. The answer to that question is no, that there are other planets. Are there other planets that have life, like on Earth? We don't know yet.
Yes.
And that's an exciting topic of research.
Exactly, and we'll come back to that then if that's, okay. Now, then there are differences among stars in terms of mass and so on, but in terms of makeup, could you tell us if there is a difference between the earliest stars that evolved and stars that are of subsequent generations from those stars? Is there anything different?
Well, let's see. There are many things that we don't know about star formation. One of the things that I guess I should mention is that stars, do form. When we look up at the stars at night, sometimes they seem like they've been there forever, but in fact, stars are forming today. Right. And exactly how they end up with the masses that they have is a big mystery in some sense. Like we know many of the elements that would go into a theory. It may depend on the initial conditions. And the detailed processes of how a star is assembled could affect the outcome mass. And then whether stars their environment could also play a role, whether they form in isolation or they form in a cluster or large conglomeration. That could make a big difference to the eventual masses. So I think there's that general question of how stars, where their masses come from, that's a big unknown. But in addition, people have already, even despite not knowing that, have tried to understand what might happen to stars in the early universe, as you mentioned.
Yes.
And there, one of the big differences between star formation today and in the early universe is that in the early universe, many of the metals, the elements heavier than hydrogen and helium, would have been very much less abundant. And because of that, the ability of the gas from which the stars form to cool would have been reduced, and as a result, people generally think that the early universe, the first generations of stars, may have been very massive compared to stars today, and so that could be makes a large difference to both how star formation develops and that sort of thing.
I see. Okay. Now, the next step, coming forward again in terms of this disk around these stars that we're all looking at now with great anticipation, I guess, is that what's in that you're an expert on the gases. Is that what it is in the disk? But I'd like to know if you can explain to us what then happens in this disk that becomes full of planets, or possibly full of planets, has the potential. How does that happen?
So we could look at our slide and continue the story, because as the material is swirling around from the outer disk to the inner disk, it's the material from which planets could form. And these disks, as you mentioned, are made of both the gas and dust. Now, by dust, I don't mean household dust that's under the bed. But dust in an astronomical sense is, you could think of it as ground up rocks, but they're very tiny. They start out as smaller than a micron in size. So these disks are full of that kind of dust and gas. And as the disk is evolving, a magical transformation could occur. And I say it in the somewhat allegorical sense, because we have a pretty good framework for how to understand planet formation, but there are many elements that have yet to be confirmed. So until we can get there, I suppose we should call this a story of how planets form. So the story is that these disks are full of gas and dust, and the dust initially settles to the midplane under gravity. And as it's moving down, it bangs into other dust grains. These are very small grains, less micron in size. And by hitting other grains, they stick and grow into larger and larger grains, eventually making rocks, and eventually what are called planetesimals, which are kilometer-sized objects. These kilometer-sized objects can collide with other planetesimals and grow into Mars-sized protoplanets. And the protoplanets, if they collide and are able to reach something like a 5 to 10 Earth mass core, within the time when the disk still has a lot of gas left, then the core can accrete a gaseous envelope and make a giant planet like Jupiter. But if it's not able to it's a race against time in some sense, and if it doesn't make it, then we might end up with a Neptune-sized core or a much smaller Earth-sized planet. And so all these, and so this general framework can explain why we could have terrestrial, Earth-sized, Neptune-sized, and Jupiter-sized planets in a solar system like ours. It's also because those are the same kind of masses that we now observe around other stars, exoplanets with those kinds of masses. It's also a good framework to understand how those systems might form.
I see. Can I just inject in there, one of the puzzles, I think, at least to us ordinary mortals, is that a lot of planets, a lot of the exoplanets that they're seeing are huge things close to their stars.
Yes.
It looks like. Does that surprise you? I mean, our bias, I think, just naturally is, oh, well, they're out there, they're out farther, and they have a job to do out farther, but the rocky planets are the ones that are in closer. Were you expecting that to?
Let's see, I guess I was definitely not expecting that. And in fact, it's a funny story about, I think, what people were expecting. When I was a grad student, I remember going to hear a lot of talks about, how the solar system formed, and how a friend of mine would, I remember him giving a talk that I made Jupiter, and it didn't work because it kept spiraling in close to the sun and was, gone. And so my theory's a failure. And I have to go back to the drawing board and try again. And of course, that's the seeds of what really happens in other planetary systems, that they might form at large radii like Jupiter, but then they spiral in very close to their stars. So if I was a little cleverer, I might have taken that idea and said, hey, there should be a lot of planets much closer to their stars. But I think at the time, many people looked at that as an example, as a reason to be pessimistic, that we would probably not find planets because they would all spiral in. But in some sense, that idea is the seed of what we actually ended up finding.
I see. So it's been very informative. I guess, do you think that there's been a lot of revision about the planetary formation, just before we go on, as a result of all the exoplanets that they're finding?
Oh yes. In fact, one of the surprising things about the properties of extrasolar planets is that they are so diverse.
Yeah.
There are planets of many different, radii very dramatically different from the solar system. Some have low eccentricities like the planets in our solar system. Some have large eccentricities. Many systems have planets much closer to their central stars than in our solar system. So understanding that kind of diversity is a big challenge. So the diversity might point to the role of a lot of different processes in the outcome. But the fact that planets are so common also means that whatever the explanation is, it must be very robust because it seems to happen all the time.
The business of this disk, again, and you were talking about these planetesimals and the fact that as they go round and round, things start to stick together. And just out of curiosity, do you know what makes them actually stick? Because I ask that because if you look at like tornadoes and dust, of course that doesn't go on for billions of years. Other kinds of things like this, and certainly if I stir up a bunch of sand, it doesn't stick together. Yeah. So is there a reason? Is there some principle that sort of governs that accretion to make things stick?
That's a very good question. People believe that through laboratory experiments, so the disks are somewhat different conditions from everyday life. They're much more rarefied. But through experiments, they find that they can grow through this sort of van der Waals force sticking and things like that to fairly macroscopic millimeter, centimeter sizes. But beyond that, it's pretty difficult to really understand how you can get to even larger sizes. So that is a major topic of research now, how to build planetesimals, because to go from very small size particles to macroscopic things is a theoretical challenge. So that's a mystery.
And it still is a mystery then. Okay, good. Well, you mentioned though the van der Waals force. Could you just tell us what that is? And does that generally apply to very small things?
That can apply to very small things, but I think the trick is to go from those kinds of forces which we understand to the uncharted territory of how to go from that size scale to very large things. So one of the projects that I think I described was whether we could look at that question from an observational standpoint, whether we could look for evidence of planetesimals actually forming in disks. I've kind of tried to take that other tack of that sort of investigation from an observational direction. So, one of the ways in which we can do that is looking at the chemistry of disks.
Yes, and that's your thing, I think, right? Is this the chemistry of the gases or the cloud in general, and you have some very interesting ways. And so, can you tell us about that?
Well, sure. So, say we were interested in trying to find evidence of these kilometer-sized planetesimals. Well, let's see. We could look at a slide here. What would we expect? Well, say we're trying to look for planetesimals that will be the building blocks of planets like Jupiter. So they'll be present in the Jupiter region of the disk, which is a pretty icy region. It's cold enough that the dust will be cold enough that water molecules will stick to them.
Right.
And so so these solids should be pretty icy. And as they grow, we imagine that they'll grow into large kilometer-sized objects, icy objects, perhaps like the comets that we see in the solar system.
So that's a distance. That's like a zone. Then you'll get these icier planets.
That's right.
Okay.
So it has to be far enough from the star, from the sun, that the solids will be cold enough that water molecules would adhere.
Okay.
So the Earth is maybe 300 degrees in kelvins, and the kind of temperature that we'd be talking about is more like 100 degrees, so significantly colder. And so these planetesimals will likely be very icy. And we also expect that planetesimals are pretty common because we see them, we see what are called debris disks around other stars.
Yes.
So disks
Okay.
of dusty debris. And that debris is believed to be produced by the collisions of leftover planetesimals that are left over from the planet formation process in those disks.
Is that related to the kind of debris, I take it, from like in the Oort cloud, or in, what am I thinking, between Jupiter and Mars?
The asteroid belt?
Yes.
So yes, the collisions
it's
of those
junk.
kinds of bodies will
Okay.
produce small particles,
Okay.
dust, that we actually can observe. So because of that, we believe that planetesimals are common in other systems as
Okay.
well as this early solar system. But the thing that I guess we don't know is whether they really are abundant enough and common enough to be the building blocks. We see a few examples, but did they really make up a large mass of the early disk? We don't know because we can't, see
right.
evidence of them directly.
Right. Do you anticipate being able to see eventually, being able to observe in that way, like you can gas now?
I think that would be very difficult.
Ah.
Because, if you think about it, these are kilometer-sized rocks.
Oh, yeah, I said you can't get a signature that they're there the way you can with gas.
That's right.
Okay.
So they might leave a chemical fingerprint
Yeah.
of their presence. So that was one of the ideas that I was investigating.
I see. And what did you find?
Well, so when, if we think about planetesimals as being full of water ice,
Yeah.
and they are the building blocks of planets, so they will be stuck, basically sequestered in the giant planet region if they're actually making a giant planet. So that means that the material that will spiral in close to the star will be deprived of water and oxygen, because the water is the primary reservoir of oxygen.
Yes.
So that makes the inner disk very carbon-rich, and a carbon-rich environment leads to the formation of organic molecules in generally. So my colleagues and I were thinking, well, maybe the signature of a disk with a lot of planetesimals is a carbon-rich signature in the gas of those disks. And a really simple hypothesis might be that systems that are really massive with high mass disks will be producing more planetesimals, and then they will show the signature more readily. So when we got some data from the Spitzer Space Telescope, which is the infrared version of the Hubble Space Telescope. So infrared is wavelengths longer than our eyes are sensitive to. We took spectra of the disks, and we were surprised, but we found a lot of molecular emission lines of water and other organic molecules. So we could test out this idea, and so we made a simple plot of organic molecules relative to water as a function of disk mass, and we found that they were related in the way that we expected. So it's encouraging that you might be able to look for the signature of planetesimals this way. And it's always exciting when you have an idea and you test it out, and it actually, so it's pretty exciting. But like for any idea, you really have to vet it with a lot of other research. So it's some years away.
But you sort of set a path there that people can then verify eventually, and you've got a large universe to look at. So
it seems pretty encouraging that we might be able to learn something about that.
Exactly. Let me ask also, would it have been possible before infrared, before you had infrared to penetrate this stuff? Do you know what I mean? I always thought that the gas, I should say the dust clouds or the molecular clouds all over the place obscured things very much. But with infrared, does it go right through?
Well, with the infrared, we can still only see the surface part of the disk, and it's kind of like looking into the surface of the sun. Like we can't see through the sun, but we can see what's on the outside, and use that to infer what's inside.
Yeah.
So it's the same idea, and the infrared is important to be able to see down that far.
Yeah.
But it's also important because that's where a lot of the relevant molecular transitions are, the kinds of transitions that probe molecules of interest at the temperatures and densities of these atmospheres, disks. So it's important for all those reasons. So without the Spitzer Space Telescope or other mid-infrared observatories, we would not be able to do that kind of research.
It's an amazing, isn't it? The Hubble and the Spitzer, I guess the Spitzer, has it just finished its mission, or
It's still going.
Something
It's still
or other?
going on its
This is
shorter wavelength.
It's just amazing. The whole history of telescopes is quite amazing, isn't it? It's developed
it's
apparently
it's
so
amazing,
fast. And radio telescopes are able to just penetrate anything, it seems like. Very interesting. Okay, so we got this planetary stuff, and you've made some great headway with that in terms of understanding what's in there. I guess do you call that the inner disk and the outer disk, or it's just one big thing?
I guess I'm saying that we were talking about the region of the disk that's very icy.
Yeah.
So the giant planet region, and then the material that I'm observing is within the inside that region.
Okay.
So inside what's called the snow line. So where it's not icy anymore, it's everything's gone back into the gas phase. So that's the region that we can study pretty easily.
I see. And then this, I guess, sort of redraws the whole idea of the exoplanets, because now you're in a position to kind of investigate the environment, is that correct, in which they're developing?
Yes, in some sense, because we have many pieces of evidence that the region we're studying is in the planet formation region of the disk. So it's a pretty direct way to study what's going on there.
Yes, okay. And then where does that lead you from there?
You mean what other kinds of things?
Yes, and once you come to this and you're able to analyze up to this point, what's the next thing?
Well, one other, another topic that we can investigate with these kinds of diagnostics has to do with the origin of prebiotic molecules.
Yes.
So let's see if
you can tell us what that is too, that prebiotic. Okay.
So
did it come up, or?
So astrobiologists have a dream that we're connected to the heavens in more than one way. As you mentioned before, the atoms in our bodies all the heavy elements are synthesized in stars, so we're related in that sense. But astrobiologists also wonder whether some of the important molecules that are what we can consider as the chemical building blocks of life might have been synthesized in these molecular clouds. So they might have been synthesized in clouds, and perhaps then, fell into these circumstellar disks, and maybe the disks processed the material further, and then these materials were all incorporated into icy bodies like comets, which could have bombarded the Earth and seeded it with the chemical building blocks of life. So one of the questions, I guess, that people have is whether how much chemical synthesis really occurs and where does it occur. So people study molecular clouds a lot to see what kinds of molecules are present there. And until recently, we haven't been able to do that much in terms of really understanding the role of the disks in this picture.
What has changed that's made it easier to understand the disks? This is really new then, isn't it, where you're at?
I think so. So before, a lot of the diagnostics that people had to study the gas in disk were restricted to the outer region of the disk that's probed in, say, the millimeter wavelengths. And when people looked at the abundances there and compared them to molecular clouds, they were not that different. And so people concluded, well, I guess disks are not really doing anything chemically, which is a little disappointing. So in our research, we were able to look at the inner regions of the disk, where the material's warmer, it's denser, and so you would expect that more chemical processing could occur. And indeed, we found some signature that it seems that molecules are more enhanced there, suggesting that disks are playing a role chemically. So it's only the beginning, of course, and so people are kind of interested to see exactly what might be synthesized there.
Right. It does sound, because this is fairly new, that being able to really analyze in this detail, the molecular makeup, it must be a very recent thing.
because we've only recently been able to study molecules in the mid-infrared.
Yeah.
So in that sense, yes.
And that's what it is. It's being able to do it in the infrared. That
I
has
think
made
that's
all the
certainly one
difference.
way to
Yeah.
have a look at it.
Right.
Uh-huh.
When you work with this kind of data, and it must be very exciting to do that, then do you also create models to go with that in your work, or is that a common thing?
Sure. Because again, we're only seeing the surface parts of the
Yeah.
disks, and you want to infer what's going on
Yes.
elsewhere. So having theoretical models of, say, the chemical structure, the thermal structure of these regions is very important if you want to draw, broader inferences. So that is also a big topic of work, and so I'm involved with some colleagues doing that sort of work as well.
Okay, but where do you go from here, and what's the biggest thing in your work that you like, that you feel like you're really accomplishing a lot with?
Well,
No, we tear our hair every day.
there's so many things.
Yeah.
One of the things is that we're also trying to use these same molecular diagnostics that I was describing
Yeah.
to look for dynamical evidence of planet formation in some of these disks. So while we expect that these disks are the birth sites of planets,
Right.
it's still pretty early days in actually trying to look for evidence of a planet in a disk. So there are a few candidates that people have identified, and my colleagues and I are trying to study the disk structure to see if that can also be a way to identify systems that are forming planets. And one of the signatures that we might look for is a circumplanetary disk. So like for example, when we look at Jupiter, it has a number of moons, and we think that the moons that orbit the planet formed from a little mini disk, just like this, the big disk that formed the star, but a smaller one around the planet. And so that the idea that forming giant planets would have these little circumplanetary disks is a very robust prediction. And we're trying to look for evidence of that kind of structure. And so we have a couple papers published where we presented preliminary evidence of that. So I'm very interested to see whether that will pan out, whether we will, that will hold up, and we might be able to see the same kind of signature in other systems.
Tell me, when you are doing this kind of investigation and modeling and projecting and all of that, are we talking years? Do you spend years and years trying to gather this stuff and analyze it? Or is it like overnight, like you just look up the stars and note that down?
Sometimes it's so embarrassingly long, Yvonne. So I think, the general ideas of the things that I've been working on are things I started when I was a postdoc.
So it does take some years for people to...
Yep. But then on the other hand, once you have, new opportunities can come at any time. So you always have to be open to them.
I understand. Just wanted to get a sense of the kind of time and commitment that astronomers have to invest in order to pursue a line of research. And then the next thing is like the things that can get in the way, like funding. Is it a problem? Like, what are the kinds of things that kind of get in the way to obstruct you from pursuing the line of work? Maybe nothing.
No, definitely. Well, let's see. Sometimes you might have a great idea, but the technology to actually do it isn't available at the time.
Yeah.
And so you have to, if it's a really good idea, you will keep trying and do the other preliminary work until the technology is ready. Or you might try to investigate it from a different point of view, like a theoretical point of view, or in this case with planetesimals, an observational point of view.
Right.
So I think it sort of, when you're struck by adversity, if it's funding or if it's technology, it can be the mother of creativity in trying to, in forcing you to think of some other avenues. But there's so many examples in science of how perseverance leads to good outcomes, as well as just, not necessarily having to wait a long time if you're just alert to a new opportunity when it arises. So I guess that's a little bit of what I've learned, and both strategies are pretty important.
Yes. And very quickly, when you are working, do you do things mainly by computer now, or are you out there, eyeballing the heavens?
No eyeball to the telescope, not now, especially not in the infrared. But so, people do a lot of work with space observatories, large or moderate-sized ground-based observatories where we take data electronically with infrared detectors or charge-coupled devices, and we do a lot of work on the computer.
Yeah.
Whether it's data reduction or theoretical calculations.
Okay, because it looks like they're sitting there in front of a computer a good bit of the time. And
you can ask my daughter what I usually do.
Okay. All right. One more thing before we go to QA is in terms of your institution, it's rather special. Would you tell us about it, please?
Sure.
NOAO.
So the NOAO is the National Optical Astronomy Observatory, and as I mentioned earlier, our mission is to provide any professional astronomer with a good idea the resources to carry out their program. And so the way we do that is people write proposals to use facilities, and they are peer-reviewed, and time is allocated, and then we assist people in carrying out the observations. We also try to plan for future instruments